So, in this session, I would like to explain about the significance of speech processing in human-centered computing. Of course, this FTP is about human-centered computing. So, in that area, that is the human-centered computing, how speech processing can play a role. So of course, I'm not working in human-centered computing field. My expertise is in speech processing. So, but from the expertise in speech processing, I will try to extrapolate something which may be relevant in the human-computer-centered computing. Of course, these are all my personal comments based on the experience. Maybe some of them you may or may not agree. I will give an introduction to this field of human-centered computing. Of course, we also have this terminology called human-computer interaction. And I also came to know about something else called human in the loop also. That is also another area where a lot of research groups are working. Then I'll give a brief introduction to speech processing. Of course, most of the talk will be on explaining about the recent trends in speech processing. So how these trends in the speech processing is making the speech processing or speech modality for the computing machines, for computing, is giving a viable alternative to the other keyboards or other modes of communication with the computing machines. So that is where I would like to bring the significance of speech processing in human-centered computing. Then I will finally summarize. Of course, yesterday some experts might have told about human-centered computing. Of course, if you see all these fields, whether you go for human-centered computing or human-computer interaction or human in the loop, the parties which will be there remains common. That is, we will have humans as a part of this what we call consortium of human, computers and environment. 3 different entities are there, and depending on what is that priority we have set, so on that basis these fields can be distinguished. However, once we understand the differences, there may be some literature where people may be using these things as interchangeably, but at the basic motivation level, their focus seems to be different.
It's okay, sir.
Yeah. So let me quickly recap. So as I mentioned in this presentation, I will be talking about the significance of the speech processing field in the proposed area of human-centered computing. And I have organized my talk like this. I'll give a brief introduction to human-centered computing. The other 2 fields, similar sounding fields like human-computer interaction or human in the loop. I'll give an introduction to speech processing. Because most of my presentation will be focused on explaining the recent trends of speech processing. This is important because the recent improvement in the performance has made the speech modality for any of these 3 domains you consider, human-centered computing, human-computer interaction, or human in the loop. The speech modality has become a very attractive alternative compared to the other modalities for communication. So with reference to that, I will hypothesize the significance of speech processing in human-centered computing, and then I'll summarize my talk. Suppose when I come to human-centered computing, if you look into the what is the distinction aspect of human-centered computing versus human-computer interaction, the distinction is when I said no, we have three entities for communication or transfer of knowledge, information here. One is human, second one is the computing machine. Computer means any computing device. Third one is the environment, external environment to which we need to interact. Means we are developed a system, computer-based system, which can take data from external environment and also serve the external environment. So that whole operating environment, it can be any electronic system itself, which is present along with the computers for doing a specific task. That whole thing I am calling it as environment. So when I come to human-centered computing, all these three components, humans, computers, and environments, will play the same level of autonomy. Okay, they can each of them. It is almost like we want. They are like peers. Equal level of communication will be there. So, however, if you see the architectures of each of these entities are quite different. For example, if I consider humans themselves, which are endowed with the cognitive system, having a large number of biological neurons and their interconnections, these human species are there in this nature, which are evolved in nature. These species, as an entity, they are designed for dealing with uncertainties. That is, we can recall ourselves the way daily basis, the way we interact with the society, external world, will have a lot of uncertainties, and we are endowed with that capability by our cognitive system to deal with that uncertainty. Okay. So, whereas when I go for deal with uncertainty means the information that you receive through your sensory organs, whether it is 5 sensory organs, whether auditory perception or visual perception or touches, taste or any other modality. So the data nature will be very fuzzy and noisy, and also from situation to situations, the conditions of the data will be different, that is uncertain. Humans, we have the capability, we have been endowed with that capability to deal with such uncertainties. So that is the hallmark characteristics of humans. Whereas when I go for computers, they cannot deal with uncertainties. Everything should be crisp and clear for them. Data, what you give should be very, very crisp data, no noisy or something. However, if you consider computers and you want to compare with humans, if you see the whole development in the computing field is to increase its computing power and storage capacity. So as a result of this, what has happened is computers are best designed entity for large-scale computing, whereas humans are not endowed with that capability of doing large-scale computing. Okay, of course, they may predict something based on their experience, but they cannot sit and do large-scale computing. Thus, can we exploit the merit or pros of humans have the capability to deal with uncertainties? Computers have the capability to do large-scale computing. Can we exploit these plus points of both these things to improve the communication or exchange of information that happens between the humans and computers? Okay. Similarly, the environment, any electronic system or any other system, electromechanical systems or control system you have designed to deal with the environment, it is essentially the goal or motive behind that environment is to best design for interaction and feedback. So you deploy that system, it will interact with the neighborhood and take the data and also give the feedback. Okay, that is that. So the very purpose of humans and computers is to develop systems to deploy in the external world to make the life better or easy for the living organisms on the universe. So in that way, that whole gamut of this environment, it is best designed for serve the society and also interact with the society and then get the feedback. So now, in that way, environment, that electronic system is best known for interaction and feedback. Thus, if I view their strengths, human strengths, strengths of computers, strengths of environments, can we exploit their strengths, best of each, while developing systems? Developing systems which involve all these three entities, that is humans, computers, and environment. But while designing and developing those systems, you exploit the best of each. Just to give an analogy for human-centered computing focus, you imagine a multi-party communication. Suppose you are interacting with few more colleagues of yours in a meeting. It is maybe formal setting or informal setting. That is what I am calling it as a multi-party human-human communication. So if you see that, when we are party to that multi-party communication, our auditory perception system or visual perception system will continuously monitor what the other members in the multi-party communication are trying to express or trying to explain. And based on that, you develop your own responses and interact with that. Absolutely, there is no mismatch. All will play dedicated level playing role to make that conversation fruitful. Okay, and the focus of human-centered computing is like that. When I am having these three things, that is humans, computers, and environment, I will design a system which involves these three entities such a way that I exploit best of each and provide a seamless integration and exchange of information among these three entities. The other thing is, suppose this will become more clear after we discuss about the human-computer interaction. The focus in human-centered computing is human. He is the party to which the both computers and environment are joining hand to come up with a good system for seamless information exchange. While designing and developing that human-centered computing systems, we consider human behavior or human characteristics as the paramount of importance. Then by considering that as the core, then you exploit the best of the other two, computers and the environment, to come up with a good system. So that is the focus of the human-centered computer. That's where it's called it is anchored around humans. So I appreciate the capabilities of humans, and I will also exploit the best abilities of computers and environment, assuming that this will be used by humans, and the whole design and development is human-centered. Coming to the human interaction, of course, this field came much earlier compared to the human-centered computing. Computers were placed at a higher pedestal, maybe late 60s or early 60s. During that time, this computer and a glorified digital electronic circuit-based system was a star attraction in all academic parlance as well as industrial parlance. Then, if you want to interact with the computer, you need a keyboard or you need a visual display unit. That is how people are using. Then people felt, how do we... So, of course, if you want to do computers from one computer to the other computer, the communication has to happen, data exchange has to happen. then we don't have to bother. But what researchers thought at that point was, can we enable these computers to interact with humans? Okay, to interact with humans, and hence the birth of human-computer interaction field came. And of course, speech modality is one important modality for this human-computer interaction. Of course, there are other modalities like gestures, online handwriting, so many things. But what is important here is to distinguish itself as a part of this human compared to the human-centered computing is the computers are kept at a slightly higher pedestal. So as a result of that, the humans who want to interact with computers should be a cooperative users for doing this, making this human-computer interaction successful. For example, if you see human-human interaction, it enables a seamless interaction, because you can recall any of the conversations that you do with fellow humans. It is a seamless interaction. Okay, you are able to make out what she is telling, and accordingly you can prepare the response and you can respond. Okay, and there is mutual adjustment, turn taking in terms of conversation. Absolutely, there is no problem in human communication. It shows a seamless interaction. Similarly, if you go for computer interaction, that is also seamless interaction. The protocols are designed, standard sets are there, data flow can happen on standard set protocol from one computer to other computer. Alternatively, when I come for human-computer interaction, it is difficult for providing seamless interaction. Okay, that is where the whole field of human-computer interaction came. How to enable this human-computer interaction? Mainly because there is an architectural mismatch, fundamental architectural mismatch. Architectural mismatch in the sense, the way humans have been evolved in nature to interact or exchange information. Similarly, the way the computers have been conceived and designed, their architectures are very different. For example, if you go for a difference, we go for, when you go for computing machines, the whole field of computing is based on stored program and data concept. That is one human architecture. Whereas if I go for humans, our architecture is experiential. That is, our cognitive system will experience with reference to a specific issue by exposing itself many iterations. Based on that, it will try to learn how to deal with such situations. Okay, there is nothing like you pre-program everything to the cognitive system and then you feed the data to cognitive system. It continuously learns. That is called experiential learning. So you can see that human-human communication, if you go, two experiential learning based entities are interacting, no problem, seamless interaction. If you go for computer-computer interaction, two one-human architecture based entities are interacting, no problem, because the same architecture. Whereas when I say unhuman versus experientially want to interact, that is where the problem comes into picture. Then the focus here in human-computer interaction was computer-centered design. Oh, I have a gadget, a very interesting gadget like computer, and I want humans to cooperate with the computer if they want to have a fruitful interaction. So that is how the thought process or design development techniques are based on that particular hypothesis. As vis-a-vis, if you go for human-centered computer, we say human. Human is at the center, and the design and development happens by keeping human as the paramount interest. We don't care whether there is an architectural mismatch or anything. So how do you exploit the best abilities of the other modalities to serve the humans? Whereas here, computer is kept at the highest pedestal in human-computer interaction. So how do I design systems better for better human-computer interaction? So that is what is the focus of human-computer interaction. Of course, this is may not be very relevant, but since this terminology is also there, I'm mentioning this. Human in the loop. Okay, here it is mainly interaction between humans and environment. And further, humans are placed at higher pedestal here. As I like anything, systems are designed, electronic, electromechanical systems, or any other type of systems are designed to operate in the external environment. And human is always in the loop to monitor and the change that comes from the operation of that system. Okay, so essentially, when human is in the loop, he or she can monitor, and if requires, change the way the outcomes will come. So that is where the significance of this autonomy comes into picture. So the degree of autonomy plays a very crucial role in human in the loop. For example, you have a designed system. You are given, assume that there are several layers of functioning of the system. Then human can decide what level of autonomy he or she can grant to that particular system. For example, you take this example of autonomous driving, okay, of the car. You can devise the whole process involved in driving on a specific road on several levels of hierarchy. Based on that, human is always in the loop. Human can grant the autonomy to this environment, and based on that autonomy level, the system will work and displays the result which is available for monitoring by the human at any point of time. But it is not that always human has to be sitting and monitoring the system. The system also can be designed to alert the human if there is any deviation happening from the agreed upon terms of conditions for operation. That is where the autonomy is given. Suppose this step 1 you have to do like this, as long as you are doing like this, and this is the typical trend of the inputs, what you are getting, you are expected, and when you process it through your system, you are expected to get an output in this range. Anything goes beyond this, then please alert me. Okay, and that is that autonomy you are giving human in that. Anything deviation is happening, the system will alert the human. Otherwise, it is operating independently. Okay, that is where the autonomy comes. That is where the human in the loop comes. Human in the loop means it is not completely always I have driven. For example, when we now do the driving of the cars, we are completely occupied while driving. When you say an autonomous driving vehicle will come, of course, you can give the autonomy to varying degrees. So as long as that it is within that agreed upon boundary condition, the system, environmental system, can take it forward to do the driving. Whenever there is a deviation, it comes back. Just to summarize, so we have these 3 broad fields: human-centered computing, where humans take the center stage; human-computer interaction, where computer takes the center design; human in the loop also, there is a lot of autonomy given to the environment. It's mainly humans and environment interaction. Computer has become part of the environment. And an autonomy is also awarded to the humans. Okay, so that is what this one. Now, coming to the, so with that, suppose when I say a human can interact with the computers or the environment only through his or her sensory organs. Okay, and all these sensory organs are controlled by cognitive system. And one of the important cognitive functions of humans is speech modality, where we can generate speech essentially to convey the message to the computers as well as the external environment. Also, we can perceive information in the speech modality. Okay, so now with using that speech modality, can I be able to design human-centered computing systems? Of course, if you go to human-computer interaction, there is a long history. As I told, one of the first areas to come up with solution was a speech modality for human-computer interaction. Since there is a long history of using speech modality for human-computer interaction, now can we view that speech modality is capable of doing human-centered computing? Human-centered computing means, suppose assume that humans are there in the whole system which you are trying to design and develop. The role of humans is monitor what is happening and then give instructions or interpret the outcomes and give instructions. That getting information can happen through speech modality, and giving instruction also can happen through speech modality. If such a thing happens, which is human himself is there, then it's perfectly fine. But human is not there. I want to replace it by a computing machine having speech modality. Whether the computing machine with that speech modality has a performance which is comparable to that of humans. If it is the case, then we can replace humans with computers there, computer-based speech systems. So the whole thing I want to review is, in the last 1 decade, the progress that has happened in the speech processing field with using deep learning as a model, deep learning as approaches for developing different speech technologies. The performance of the speech technologies based on deep learning seem to be reached that human level performance. As a result of that, we may be able to use computer-based speech technologies while designing and developing human computers, human-centered computing systems. So to appreciate that, we need to know what is happening in the speech processing field. As I mentioned, when I take speech, it is an important cognitive function. Our human cognitive system is good at modeling information present in the speech. Okay, it can learn from the experience. The information that is coming through the speech signal can be learned by the human cognitive system, and then based on that learned experience, it can also produce a speech or give out the response in the speech modality. And that is the important things for the this one. Okay, sorry. Okay, so with reference to that, whereas when I consider a whole journey of human-computer interaction that has happened for last 6 decades for using speech modality, we are trying to mimic the speech modality of human interaction on a computing machine. We are only trying to mimic because even though we are endowed with this capability of producing speech and perceiving speech, it is not very clear. No, it is not algorithmically. Of course, we can say approach how it is happening, but at the neuronal level, how this experience is learned and modeled is not still very clear. So for that purpose, only we try to mimic that process. Mimic means you just duplicate that activity, but may not be exactly the way humans do it since we have not understood. Okay. So, of course, for human-computer interaction, computing machines were trying to mimic this activity to enable speech modality of interaction with the computers. Of course, the approaches which were before 2010, they were able to demonstrate the feasibility of using speech modality for interaction with the computer. And all these approaches, their performance was not at par with the human performance. When it comes to speech processing, same thing with reference to vision also, the benchmark we have is human subjects itself. Suppose I produce a speech in a specific agreed upon language, and the person who is taking the notes is a human who is proficient in that language. And also I have a parallel computing system where a speech recognition system, automatic speech recognition system is loaded onto that. Now that is also listening to you through the microphone, and there is a human subject who can write down your notes to convert into text format. Now you produce speech which is simultaneously taken in by the computer as well as the humans, and in the end you find out how many words errors have come in the human subject as well as in the computers. Suppose in the PRML case, especially in practical settings, the PRML approach's performance measured in terms of word error rate was seen to be much inferior compared to human expert. Whereas by using deep learning in the last 1 decade, we are able to develop some speech technologies where these technologies have given comparable performance to humans. Just for example, I say humans themselves make about 3% error while writing down the message part from the speech. The deep learning system is also able to do such things. Okay? That means to say, if I wish, I can indeed replace a human with a computer-based speech-based computing system to play the role of humans. That is one way of viewing. The other way is the computers will be able to better interact with humans now via speech modality, because the speech-based systems stored on the computers have capability like any other human subject to decipher the message that is spoken by the human operator. So that means to say, these computers enabled with speech technology are equipped for giving a better message or exchange of information between humans, computers, and the environment in the proposed human-centered computing field. For example, if I take human-human communication, so just a final statement I want to make here, that with significant improvement in the performance of speech technologies, automatic speech technologies based on deep learning, now it is all the more feasible to use computers loaded with automatic speech technologies to give a better seamless interaction with humans as well as the environment. That is what I wanted to say. Earlier, before 2010, where we had all this pattern recognition machine learning approach, there is always a degree of uncertainty about the successful interaction that may happen between humans and computers. That is no more the case nowadays. Okay, so that is the positive point I want to say about the latest development in the speech thing. Coming to the human-human communication, if you see, you can have a oral mode of communication, which is, it can be either verbal or non-verbal. Verbal communication of the oral part involves the spoken language. I produce message in the spoken language of a specific thing. Alternatively, this non-verbal communication will have laughing, crying, coughing, etc. Even though they don't, the advantage of spoken language is there is a specific language backing this column of verbal communication. That means to say there are a set of valid words in that language and there is a grammar associated with that. And that arrangement makes us to convey a large amount of information in a seamless manner using the speech modality. Whereas when I go for non-verbal communication, which involves laughing, crying, coughing, etc., of course, they are essentially meant for expressing something in a non-verbal manner. But if you want, at least to a limited extent, you can code the information and try to convey through these modalities. Okay, and these are all characteristics of oral communication. When I come to the non-oral communication, it can be, again, verbal communication you have written language or sign language, where again it is backed by the language. And non-verbal, we have what are called gestures, body language, etc. So we use one or more of these when we are doing human-human communication. Okay? And all of them are cognitive activities. Spoken language interaction is a cognitive activity. Laughing, crying, and coughing is a cognitive activity. Written or sign language interpretation is a cognitive activity. Similarly, the gestures or body language is also a cognitive activity. So in that way, you have a multimodal aspect of oral and non-oral communication, which is exploited in human-human communication. Now, with such an improved performance in the speech modality, can we try to use this knowledge for designing human-centered computing systems which can provide improved performance compared to what were having earlier? Okay. So in that motivation, if you see the recent results in the commercial deployment of the speech technologies gives confidence in that direction. Of course, this was a dream for a long time, starting from early 1960s. People have always dreamt of creating computing machines that can recognize the speech, means recognize the message present in the given speech signal, or recognize who is that person by listening to his or her speech signal, or they can generate speech by themselves, which enables human-computer interaction seamless. Of course, for several decades, it was proven to be hard due to the very cognitive nature of speech communication. As I told earlier in the previous slide, even though demonstrations were available till the last decade, became commercially successful very recently. For example, you might have watched the video or advertisements on Amazon, Alexa, Google Home, and so on. Even Apple Siri was there sometime. So these speech technologies have matured enough where humans can interact with them to do certain activity. That means to say they can treat them as another party in the multi-party communication. Okay, so that brings us to an advantage for using the speech modality for human-centered computing system. Of course, the whole effort in the last one decade is how do I develop different speech technologies. Initially, it started with speech recognition, then moved on to speaker recognition, language identification, speech synthesis. The whole effort in the last decade is how do I improve the performance of these independent technologies such that I get an equivalent performance that of human subjects. That has been achieved in many of the speech technologies. So then that also created a lot of interest in speech processing area by the different community. But what is interesting will be how do I use such an advanced system, a computing system, which can provide a seamless interaction with humans in human-computer interaction via speech modality. How do I exploit this result that is available in human-computer interaction to build human-centered computing systems? Of course, whether it is, this progress is only just a bubble on the surface or it is a deep driven. Yes, it is a deep driven technology. This is completely backed up by what is called deep learning. And it has been shown beyond doubt by commercial deployment of many speech recognition technology like Amazon Alexa and Google Home, where people can interact with that. You don't require any pre-training to use those devices. Okay, so to that extent, they are robust. That means to say, definitely this speech modality based computing systems can do a better job when I'm using them in the human-centered computing aspect. So that's whoever is interested in working in human-centered computing can exploit this latest trends in speech processing, conventional speech processing area, to bring it to human-computer centered computing for designing better quality systems. Of course, the success of deep learning, if you see many of the terminologies in the deep learning, they claim that this is because of this very interesting architecture we have. That's where the improved performance is coming. But it is also equally true that these deep learning architectures were there long back itself, about 30 years back itself. Convolutional network, recurrent neural network, long short-term memory, all these things were there earlier itself as advanced topics in neural networks. But now why they were not successful at that point, why they are successful now, that is mainly because of the timing, where we have very powerful computing infrastructure like graphical processing unit, GPU, and a lot of digital data now available, either in the open source format or getting distributed from some agency which can be used for. Earlier, it was a difficult task to collect data because deep learning models are data hungry. You need large amount of data. Fortunately, because of this connected world, we can collect any amount of data. Okay, so the success of this deep learning based speech technology can be equally attributed to the developments in the computer architecture to come up with these GPU architectures, and also availability of large amount of digital data at a very throwaway rate, okay, or price. So as a result of that, we have computer-based speech technologies which provides human level performance. However, if I want to use it as a part of human-centered computing, it is still a long way to go. When we are looking for this deep learning, we also use these terminologies like artificial intelligence, pattern recognition, machine learning, and deep learning. Many times we use them as in a combination, or we can use them as interchangeably. However, we need to understand the basic differences between them. After that, there's no problem. If you want, sometimes you can use them interchangeably also. So depending on the scenario, we can interpret what exactly you mean. Suppose this field of artificial intelligence was there long back in the computers, where all the attempts that have been done by the researchers to enable computers to perform intelligent tasks. Intelligent task means it is not only IQ testing or something. Even any task that humans do to survive in this nature or in the environment is an intelligent task. Of course, to that extent, other animals also have been given that ability of intelligence. However, humans are the most evolved species. Okay, so as a result of that, we are able to perform intelligent tasks. Intelligent task means it is as simple as knowing the route, registering the route in my mind or cognitive system of traveling from point A to point B. This is an experience for us. Suppose when I'm going from my house to my working place for the first time, the whole path seems to be very new for you, and you will not be able to recollect how exactly you reached from your home to the office. After few days, when you are repeatedly moving through the same route, your cognitive system will develop or experience that the sequence of points coming through for that travel. So as a result of that, it registers the path from your home to the office. And that process is an intelligent activity. Similarly, suppose I want to learn driving. First day it will be very horrible, but after several rounds of training session, I will be able to handle I become experienced driver. And that is also an intelligent activity. Like this, anything as humans we do, we will not be proficient on day one. We learn through time and mistakes, and based on that, I will be able to do. And all of them, and that is what I'm calling it as an intelligent task. Now, since humans can do, can computers also can perform those intelligent tasks, and hence the birth of this field of artificial intelligence. Okay, so where, of course, when I learn driving of a vehicle, first day when I go to the driving school, I will be very scary. I should not press in place of brake. I should not press the accelerator. I will always have that fear in my mind. By mistakenly where I am supposed to vehicle, I push the accelerator, then I am gone. Okay, but after some time, when you become experienced person, then no, the autonomy is granted to the particular leg itself, where he can handle those interactions at that level itself. Okay, and these artificial intelligence approaches, since that experienced way of learning cannot be really coded step by step, because each person will have their own way of learning this driving. So accordingly, we can only mimic that activity on a computer, and hence the birth of the field of artificial intelligence came into picture. One way of doing artificial intelligence is we can do pattern recognition. Pattern recognition, essentially, to appreciate this pattern recognition, we need to appreciate the difference between pattern versus data. Data is some set of values that we give it for computers for processing, whereas patterns is some representation that you can create using this data to interpret by any of the to interpret this information, and such a thing is called as pattern. For example, if I have taken my mobile phone and shot a photo either of my friend or through an external environment. Suppose if you, by looking at the face present in the image, you will be able to identify who is that person. Suppose he is known to you, or it's well-known public figure. Alternatively, if I want to just load it onto the computer, it is just a two-dimensional array of numbers. Okay, and that what you perceive through your cognitive system using any of these sensory mechanisms is called as pattern, whereas the two-dimensional data what you have is called as the data. Okay, so pattern recognition field again documents all the effort that have been made for recognizing patterns in the given data. Okay, you see the difference between pattern and data, then only you will appreciate this field of pattern recognition. So this pattern essentially refers to the entity that we get to sense through our 5 sensory mechanisms is the pattern, whereas just the two-dimensional data or multi-dimensional data is data, or values is data. Okay, just by opening the file, having this data values, you will not be able to make out about information about the message part. Alternatively, coming to the machine learning, our goal is similar to that of the pattern recognition. However, in the pattern recognition, in the machine learning, we want to learn the underlying pattern that is there in the given set of features without being explicitly programmed. So this is a very slightly controversial statement. Without program, how you will run a machine learning model? See, training a machine learning model or testing a learning model, that program I'm not talking about. You have to do that if you want to do it on a computing machine. But I can use a machine learning tool like support vector machine, which in its basic form we will have this binary classification modality. The learning process of support vectors in the support vector machine should need not be documented or hardwired into the code. Suppose when you're using the support vector machine for speech processing like this, you always better follow that protocol. That is that the underlying pattern learning, the same program of support vector machine should be able to identify the support vectors. Since I am not hardwired for a specific domain, it can extract that information and use that. So that is why it is called as machine learning. To summarize, when I go for machine learning, we give the flexibility for the model or the learning algorithm to discover the underlying pattern. Whereas when I go for pattern recognition, Sunit Verma, can you mute your mic? Okay. So when I go for machine learning, we are not explicitly programming on what underlying pattern to learn. That underlying pattern can be anything. You give the set of data points and it learns the underlying pattern or function. Mathematical way, it is a function. Whereas in the pattern recognition, usually we say, okay, this is the pattern you are looking for. Of course, there is now later days, there is not much distinction between pattern recognition and machine learning. But if you want to ask one thing which is a different mean, we will say what pattern to look for. In the machine learning, we will not say what pattern to look for. There is a pattern, you learn it. That's what we say to the machine learning. Whereas when important thing, machine learning, unless specified, as opposed to deep learning, is in case of machine learning, you are given set of features and being advised to learn the underlying pattern information or functional information. Whereas when I go for deep learning, even features are not extracted. You can either directly give the raw data for learning, and using that raw data, initial few layers of the deep learning model will extract the representations, which are nothing but the features in an indirect way. And these features are then used for modeling. Or that is also goes through the deep learning, where essentially the functions are, what functions to learn is not explicitly programmed, but you can learn that. Okay. So if you see the broader objective, artificial intelligence goal is to perform intelligent tasks. Recognizing pattern is an intelligent task. Whether you want to recognize explicit programming or implicit programming, we are all dealing with intelligent activities. So in that basket, we can indeed use these terminologies, AI, PR, ML, and DL interchangeably. But there is a distinction among these four fields. But having said that, if you want to, just to summarize, deep learning, you can directly feed the raw data and learn the pattern. Machine learning, you feed the features and learn the model. Whereas what to learn is not clearly specified. In pattern recognition, you give the features and also said what to learn. Okay, that is recognizing the patterns. If you see the major milestones in the speech processing, which happened earlier, there are several important things development happened. Initial attempts in the speech processing to do human-computer interaction was coming up with clustering methods. You are given set of data points. You do the grouping of those data points and assign a label for that or use that knowledge for further processing. And then the clustering is a spatial organization of the data points and trying to model that. Whereas we had this dynamic time warping where you want to match two temporal sequences of different lengths. Then I can make use of the dynamic time warping. Then we have this stochastic model like Gaussian mixture models and hidden Markov models. When I come for Gaussian mixture model, it is also grouping the data, but using a stochastic model, which is called as a Gaussian mixture model. Again, it's a spatial distribution of the data point. And the next one is a hidden Markov model. It's a time series modeling of data, which we can say a combination of dynamic time warping and Gaussian mixture model will give you hidden Markov models. Okay, so that is that hidden Markov model case. Then the next one came in the field was the neural networks, where you have a parallel and distributed neuronal elements. Using that, you can process the features to model the class information. Then came the support vector machine, where the classification principle is different, where it is a maximum margin classifier, where you can learn the maximum margin separation between the given set of positive class of examples and negative class of examples. All these things are mathematically well tractable and very interesting approaches people have developed. What they have done is they have demonstrated the feasibility of building speech technologies using these models. However, their performance was not at the level of what we get like a humans. It only demonstrated the feasibility, but their performance was much inferior compared to what we used to achieve by deep learning models. Okay, so that is where we cannot deploy practical systems which can operate in all the conditions using that. Whereas in the last 1 decade, where we have different deep learning models, many deep learning models have been proposed, which includes deep feed-forward neural networks, deep belief networks, deep autoencoders, generative adversarial networks, convolutional neural networks, time delay neural networks, recurrent neural network, long short-term memory neural networks, transformers. Many deep learning models have come. All of these have shown their potential for modeling the information present in the given raw data in a much more involved manner, much more deeper manner, such that I can use that model as a robust model for deploying in practical settings. Okay, so that is where the success of this deep learning model based speech recognitions, which has been exploited in Amazon, Alexa, Google Home, and those things. Okay, of course, every now and then new deep learning models comes. Their architecture supported by the large computing power given by the graphical processing units and large amount of digital data available. All these three fueled developing robust systems for speech technologies. Okay, so Suppose if I take the previous literature, where one of the successful model was Gaussian mixture model, hidden Markov model. This was the most successful model for acoustic modeling, which is an important component of speech recognition. That is, what we in a conventional terminology we call it as phoneme recognition system. Okay, these till this advent of deep learning models came into picture, this Gaussian mixture model seems to be one of the most successful models for acoustic modeling, and their performance was not beaten by even shallow neural networks. Alternatively, people have shown that using the deep learning models, like feed-forward deep neural networks or any variants, we are able to get the performance of acoustic modeling system much higher than what we used to achieve by GMM-HMM system. Taken from this paper, if you see, what is important is just the numbers. Suppose if I go for Gaussian mixture hidden Markov model, we had a phoneme error rate. Phoneme is the basic sound in a language, we call it as phoneme. It has a phoneme error rate of about 27.3% for timid database. Numbers are not important. The relative things are important. When on a timid database, when they did that acoustic modeling using GMM-HMM system, it has a phoneme error rate of about 27.3%. Okay. Now, the initial version of the deep neural network model they used using randomly initialized weights gave an improvement of about 3%. Okay. Further tuning using deep belief networks architecture and doing greedy layer-wise training, it further improved by another 1%. And finally, replacing DBN with convolutional DNN on filter bank energy gives about 20%. So what is important is also from 27% to 20% we have come. Is it good enough? Yes, it is indeed, because for a long time, about 1.5 to 2 decades, we have a stagnation in this system performance. Always, even support vector machine comes, their performance maybe on some data set will be hovering around 27.3 only. There is no further improvement happening. That is where it attracted the attention of the speech committee. Suddenly, there is an absolute jump of 7% performance, which was good enough to push the automatic speech recognition to the next level, their performance to the next level, so that we can use them in practice. So when you go for this automatic speech recognition, it deals with recognizing spoken message. Means we are interested in knowing what is being spoken, and in a layman term, we call it a speech to text conversion. Essentially, it will write down what I say. That is the thing it will happen. And the PRML approaches, which earlier used, as I mentioned, we used to exploit clustering, dynamic time warping, and hidden Markov model. Whereas deep learning, we are using these deep neural networks and deep autoencoders and other things for building automatic speech recognition systems. We need not go for the detail how we are developing. See, there was a word. Now, speech recognition system performance are measured in terms of word error rate. This word error rate for GMM-HMM system was 23%, whereas it came down to 16% by using the deep neural network model, which is roughly about 8% improvement in the performance, 78% improvement. As done in the acoustic modeling, same thing getting reflected in the word error rate also. Of course, these are much more practical data sets. It should be late. This result is in 2012. I'm sure the latest results will be much more than this. Okay. And that improved performance fueled deployment of speech recognitions in the field. Okay. So as a result, that is the result of this Amazon Alexa or Google Home. So that shows that these using deep learning, we are able to bring speech technologies which are much higher capabilities compared to the earlier versions using pattern recognition machine learning. Similarly, if you consider other fields like speaker recognition or language recognition, when you come to the speaker recognition or language, the goal is to recognize the speaker or the language. Essentially, we're interested in who spoke or which language it is. That is the interest. In the PRL approach, again, we are using those models. One of the special attraction for the speaker language recognition was the Gaussian mixture model and the I vectors. And it is being replaced by the deep learning architectures, which involves deep neural networks, deep autoencoders, and X vectors. Again, here you see, if you go for speaker recognition, we had this I vector based system, which was giving an equal error rate of about 7.45%. And which was by default was using Mel frequency Kestrel coefficient as the features, which was replaced with high vector bottleneck features. Bottleneck features are extracted by the deep autoencoder from the bottleneck layer. It further improved the performance. Again, instead of going through this GMM to derive the high vectors, we can do the derivation of that I vector directly using the deep learning model, which was called as the X vector. That also further improved the performance. Same thing on a different data set, the same trend is observed. What it shows is the deep learning models have pushed the origin of performance origin of all the speech technologies to the next level. Step change has come, which is comparable to that of the humans. For the speaker recognition, humans' performance also will be hovering around the same point under difficult conditions. Similarly, for language recognition also, there is significant improvement in the performance. Same way, coming to the speech synthesis, this is another important area where earlier we struggled to generate speech from a computer. We can store and playback. That is not speech synthesis, but I want to derive or generate speech data from the features without any samples of the speech, in the sense waveforms being stored. That is the challenge for the speech synthesis. Earlier, we had several things by hidden Markov models and concurrent synthesis. So performance was not comparable to that of humans. Anybody listening to the speech can make out that it is a synthetic speech, computer. Whereas the deep learning approach models, which have been like WaveNet, Tacotron, Deep Voice, Character to Wave, they have really pushed the boundary where it is difficult to distinguish whether this is a computer-generated speech or a human-generated speech. To that level, their performance has improved. For example, earlier on a 5-point mean opinion score scale, we were hovering around 3 as the mean opinion score. Okay, this was not suitable for commercial exploitation. Whereas the recent ones, like suppose you take WaveNet or LSTM or WaveNet, if you take the best performing system, it gave a performance of about 4.21 on English. Whereas the human subject themselves, their speech analysis will give you 4.46. Means if I am listening to the natural speech, that also gives me a mean opinion score of 4.6, whereas WaveNet gives me 4.21, which is comparable. All our mobile phones is around 3.7, the quality of the speech signal. So that way, the quality of the speech signal generated is also very good. So now what it says is, okay, so what is the implication of all these significantly improved speech technologies? For human-computer interaction, it is directly obvious. Any improvement in the performance will improve the human-computer interaction system. But what is its impacts on human computing, human-centered computing? Suppose, coming to the performance level, suppose as a human in a multimodal way can interact with the human-centered computing system. I can use visual mode of interaction, gesture mode of interaction, any other mode of interaction with the human-centered computing. We can, the speech technology has matured such that the performance of speech technologies is comparable to that of human level performance. since the performance is comparable to human level performance, therefore, in a multimodal interaction of human-centered computing, we can indeed exploit the speech modality, if possible, for designing and developing human-centered computing systems. The second important point is the data rate of speech signal is significantly small compared to, say, video. Very, very small. So as a result of that, with a less overhead, I can do the communication by using speech modality. Third one is, suppose if I want to go by sign language mode of interaction, the centered computer, somebody has to be specially trained. Whereas when I go for speech, it is a fundamental mode of communication. Since it is a fundamental mode of communication, it is an effortless mode of communication, public can easily adopt or use that in the developed human computer-based system. Also, since the computers now are endowed with this latest speech technologies, computer can play a level playing role by adding speech modality. Thus, it can interact better with the humans, which are there in the human-centered computing systems. These are some of the points which push us or advise us of using speech modality in human-centered computing. To summarize, there is a significant progress that has been made in adding values to these computing machines, in making them to handle more intelligent tasks. Even speech mode of communication is also, mode of interaction is also an intelligent activity. Starting from pattern recognition, the latest trend is deep learning. Okay, so in all these things, we have made a lot of progress, and this latest trend in deep learning is producing speech technologies having comparable performance to that of the humans. So this deep learning resulted in several speech technologies that can be used for practical deployment. Now, if you say, then what next in the speech processing area? I can say the tasks that were easy for a person to do effortlessly. For example, I do speech recognition. For example, in my mother tongue, I can interact with any person. That person need not have a formal education, or he or she need not know computers. That means to say, these are all very effortless tasks for humans. Now, those can be accomplished now by deep learning, provided you have enough, given sufficiently large models and large data sets. Whereas the tasks which are not well understood, for example, human-centered computing, system development for a specific task, which is not still well understood, is beyond the scope of this deep learning improvement that has been achieved. Thus, the human-centered computing can be treated as an application area where we can try to see how this latest trends in speech processing will indeed be useful for building human-centered computing systems. I think with that, I will conclude my talk here. Thank you very much for for your patient hearing. I'll be very happy to take some questions. If I know, I will try to answer. Any questions?
Participants, ask your questions, please.
Sir, could you explain the difference between machine learning and deep learning once again? That how can we understand that like if I have a convolutional neural network, after how many hidden layers will that network be known as a deep network, or otherwise it will be a shallow network?
Okay, thank you for this question. See, if you see deep learning, that is a specialized version of the machine learning, where when you use a deep learning model for doing any of these machine learning tasks, that we call it as deep learning. So in that way, machine learning is a bigger umbrella under which this deep learning comes into picture. without taking this convolutional network or something as an example, in a general thing, I want to understand the difference. Maybe I may have to share the screen, and let me go if there is any. Just give me a minute. Sorry, there is some. Okay. So, suppose whether you consider pattern recognition or machine learning or deep learning. Oh, sorry, there is something. Okay. Any of these things you consider, the goal here is you are given data points. You are given data points where y is the output, where which is related to the f by a sum function. And the whole journey of pattern recognition, machine learning or deep learning is what is that functional relationship that exists between the input and the output data point that we need to learn. Okay. So when I go for pattern recognition, I tell what is this function exactly, and the whole learning algorithm is to derive that function. Whereas when I go for machine learning, I will not know what function to learn, but I know that given this data point, there is some functional relationship that exists between the input and output that I want to learn. Okay, so what exactly that function, what is the nature of the function is not known, but it is said that yes, X is the input to the system and Y is the output. Now you find out the functional relationship. That is now learning that implicit function which is not explicitly stated is machine learning. So in that direction, deep learning also is a machine learning type. Okay, so in that way, if you look into the task objective, both machine learning and deep learning deal with learning the implicit function that is there between the given data points. Okay. Whereas the distinction, what it comes for machine learning and deep learning is, when I go for machine learning, I use features as the starting point. The input X represents the features. Whereas when I go for deep learning, it is mostly raw data. The input X is the raw data. So as a result of that, what we need in the deep learning model is, first few layers are required. When you feed the raw data, first few layers are required to process this raw data to get the feature representation. Then you pass it through further few layers to do the machine learning or functional learning. Okay. So since we are trying to learn the representation itself from the raw data, the name deep learning comes into picture. Of course, we also, one of the reason also due to number of layers we use it in the deep learning model, but that is not the only reason. Since we are going to learn the features also from the raw data, it is deeply learning the information. That is why it is called as deep learning model. Coming to the next question, what you asked, when do I treat it as a shallow network or when do I treat it as a deep network? One way, suppose if I take a feed-forward neural network, if you look into the theory, a multi-layer perceptron. If you take, there is one input layer, there is one hidden layer, one of the
Sir, your
perceptron.
screen is not visible.
Sorry. So you have, this whole thing was not visible when I was explaining.
No, sir, it was just 1 minute prior.
Okay. So when I go for multi-layer perceptron, input layer is there, hidden layer 1 is there, hidden layer 2 is there, hidden layer 3 is there, and output layer is there. Okay. So if you exclude input and output layer, there are all these 3 layers are perceptron layer. Okay. Now what is said is, if you take 3 hidden layers, it is sufficient to model any complex pattern. So that is how the whole theory behind shallow feed-forward neural networks has come. Then, if you increase the number of layers beyond 3, in the era of shallow neural network, you are not gaining any improvement in the performance. Then people said that no, there is no point in increasing the number of layers. But when the deep neural networks came into picture, what was found out was the backpropagation learning algorithm, which is one of the important workhorse algorithms in the neural networks, had what we call vanishing gradient or exploding gradient problem, which resulted in when I propagate the errors from the output layer towards the hidden layers in the input towards the input layer, you will not be able to adjust the weights here, because the error which is propagating, they might have vanished by that time, or it has exploded, which has no meaning. That is where people have mostly stopped at 3 layers. But with these deep learning models, you can go beyond 3 layers also. There is no hard and fast rule for the number of layers, or there is no marked boundary between shallow and deep neural network. If you specifically press me and say, no, you give me a number, anything beyond 3 hidden layers can be treated as we are entering into the real realm of deep neural networks. Because in the traditional shallow feed-forward neural network, beyond that you end up in this problem of exploding or vanishing gradient issue. Okay, so that is the most generic answer I can give.
Thank you so much, sir.
Okay, any other questions? Any other questions?
Any other questions, please? Any other questions, participants? Sir, your screen is shared.
Yes, Jyoti?
Sir, your screen is shared.
That's okay. I just wanted to send you the slides, otherwise I'll forget.
Okay.
I have sent the slides. Okay.
Sir, there is a question. Is it always needed to use hidden layer for desired output?
Yes, definitely. See, hidden layer is the because without hidden layers, the type of pattern recognition or machine learning task which you can solve will be very limited. If you want to deal with a very the classes that are separated, which are non-linearly separable classes, which are all distributed in a non-convex manner, then you need hidden layer.
So how much requirement do we have for an attention layer in a speech recognition? Do we need to build a trust-based system over in the speech form also? Like currently we have the explainable AI, the major concept, the attention layers to understand the relation between the features and the output. So will that be a requirement in case of the speech recognition?
See, there is nothing like that, but people have found that with the help of this attention, you are able to give more knowledge about long-term information. So as a result of that, this added some value, but it's not a prerequisite that you need to use attention for speech recognition. Only thing is that is additional features that have been incorporated into the deep learning models. That attention feature also seems to be helping, means a long-term attention you are giving. For example, when I'm doing speech recognition, human-human speech recognition, it is not just I'm locally concentrating on to few frames or giving understanding message. Maybe I will also look into a lot of history about that phrase to understand the message. So that is where the advantage of this attention is coming into picture. It is an additional feature. If you use it, is good, but it is not mandatory always.
Okay. Thank you, sir.
Okay.
So are there any questions, participants? So we hope there are no other questions. So I'd like to thank you, sir, for your thought-provoking talk. It was a great experience to hear from you, sir. And thank you, sir, for your time out of your busy schedule and giving us the opportunity to learn from you. And it is really a blessing. And I would like to thank you from the entire human-centered computing FDP team and EC department and as a whole from Guwahati University family. So thank you for being with us.
Thank you very much. Thank you very much, Jyoti. Thank you all the participants. All the best for your workshop. Thank you very much.